Hey, what's up, everyone? Welcome to States of Matter Part 3. And today is going to be all about liquids, vapor pressure, and our phase diagrams. Um, so, if you look at the molecular model of a liquid, you'll see that there are particles that are moving around. And although it's not like a solid where all they can do is just vibrate around, they can move a little, they cannot move a crazy amount. Definitely not as much as a gas can move around. So they are somewhat stuck in their position. They can move around a little around their space, but not really make any drastic movements. And these lead to some interesting properties, such as they have a definite volume, they have indefinite shape, they can be slightly compressed, and the change in pressure from that slight compression is minimal and it requires enormous pressure. So although it can be slightly compressed, it's not very common. And then you're going to have things of surface tension and capillary action. So a lot of these properties are kind of intuitive. Like if you have some water in a glass versus water in a cup, the shape is going to be filled up differently, but the volume is still going to stay the same. And that's what definite volume and indefinite shape mean. Let's start going over 4 and 5, which is surface tension and capillary action that are very important to liquids. Firstly, you have surface tension. So surface tension is a resistance of a liquid to increase in its surface area. And a prime example of this is if you ever see like a waxed car, the water droplets on that waxed car will beat up and they become this circular shape. And that circular shape is a resistance to increasing surface area. If the water were to collapse and go all over, the surface area increases a great amount compared to the surface area you would have if it was just a sphere. And what's keeping it a sphere is its intermolecular forces. The intermolecular forces don't want to break and they keep together so that they can create the circular shape. Another example of it is if you've ever seen those bugs on water, what they're taking advantage of is surface tension. The water doesn't want to break its intermolecular forces, and the weight of the insect is not enough to break it anyway. So what you see are those dimples instead of actually the bug just going underwater. And so as you increase your IMFs, your intermolecular forces, your surface tension goes up. So if you have stronger liquids, liquids with stronger IMFs, you're gonna experience more surface tension. And that's why water in particular has such high surface tension, because you see a lot of hydrogen bonding in water that makes it a very strong substance. The second property is capillary action. And capillary action is the spontaneous rising of a liquid in a narrow tube. So um, usually polar molecules are going to exhibit this. You can see on the left here, the diagram shows how the water is rising above the level of the water that's in this solution. And so what is causing this? Well, there's mainly two things. First of all, cohesive forces, which are the IMFs between the molecules, right? So as one molecule goes a little up, the IMFs push the other molecules back up on the level that that molecule is on. And then they create this chain reaction where they just keep continuously going up. And then you have adhesive forces. So the water sticks to the side of the tube, and then since it sticks to the side, all the other molecules want to be at the level that the molecule is on because of the cohesive forces. So really adhesive and cohesive forces work together to create a chain reaction that causes the water to rise up in level. And you might notice here that in a wider tube, the water does not rise up as much. And that's because the water is resisting gravity. If you have more surface area for gravity to work on, then the water can't get as high because gravity in that area is so strong. On the other hand, if you have a low surface area that's exposed to gravity, then the water level is going to be higher. One of the most important uses of capillary action in nature is the transportation of water in plants. So what plants do is that they absorb water through their roots, and they're I think they're called xylem or something, but they have these super narrow tubes that are very small, and they use capillary action to deliver that water to other parts of the plant. Okay, so now that we've taken a look at a lot of the properties of liquids, let's take a look at what vapor pressure is. So imagine you have a container full of, say, water molecules. You just have a bunch of them, and they're all moving around. They have kinetic energy, and you can probably plot their kinetic energy in some graph like this. So a lot of them are going to have this amount of energy, but energy, like the amount of kinetic energy that they actually have is distributed. So although you can have an average kinetic energy, different particles are going to have different kinetic energy. And so what happens to this container of liquid is that, by the way, the black line here is the surface level. It's not like a container. So the water is just the surface level, and then the container is the actual box itself. So what happens is that some of the molecules of water that are on the top are going to by chance have enough energy to jump up above the surface and become vapor. So if we take a look at the kinetic energy graph, and we say about that much kinetic energy is required to escape the surface, then the particles that are at the surface that have that much energy or more, the particles that are over here on the graph, they're going to have enough energy to jump up above the surface and become this vapor. And so it's important to recognize that although some of the vapor here might have a lot of energy, in a similar way, at some point they might lose a lot of their energy, and because of that, they're going to fall back down into the container. But really, this is a continuous process. So some are going to have enough to jump up, and then some are going to have very low, so they're going to come back down. And it's just this dynamic equilibrium at some point. So now let's see what happens when we increase the temperature, right? We start off with a distribution that looks like this, and the line is right here. This is the line, this is the amount of energy you need to escape the surface of the water and become a vapor. What happens when we increase the temperature is that this line, the position of this line does not change. Although it might look like it on the diagram, is because it's a shitty diagram that I made, but the position of the black line does not change. What changes is this bell graph. So this bell graph shifts to the right when you increase temperature. The amount of energy required to jump up from the surface doesn't change. What changes is the amount of particles that have enough energy. So in this case, you have quite few particles that have enough energy, but in this case, you have a lot of particles that have enough energy. And so what does this look like on the molecular model? Well, you have your normal one where only a couple are going to go, and then when you increase the temperature, you see that more of these surface atoms are going to jump up and become vapor. And so at equilibrium, the rates of condensation and vaporization are equal. So when you're at an equilibrium, the amount of molecules that are jumping up and the amount of molecules that are jumping down are going to cancel each other out. And that is what you call a dynamic equilibrium. And so the equilibrium vapor pressure is the pressure of that vapor at equilibrium. If you let that system go to completion, or equilibrium rather, the pressure that the water vapors create is going to be known as the equilibrium vapor pressure. And it's very commonly just referred to as just the vapor pressure. And so you have volatile compounds and non-volatile compounds. Volatile compounds are compounds with high vapor pressure. So that means a lot of them are going to jump up from the surface of the liquid. But on the other hand, if you have a non-volatile compound, these are compounds with low vapor pressure. So on the top, there's not going to be as much vapor. There's going to be a lot less vapor than there are in volatile compounds. And there is actually a relationship between the vapor pressure and the boiling point. When the vapor pressure is equal to the pressure of the atmosphere, you have reached the boiling point. So in this model, you have atmospheric pressure that's pushing on it. And eventually, when you have enough molecules that are over here and can resist that push, then you have reached the boiling point. And so think about what that means, right? We could have a higher pressure by either increasing the temperature. Increasing the temperature will let more of these molecules jump up, or we could decrease the volume of this gas area. So although you have the same number of molecules that are jumping up, the volume is less, therefore the pressure is higher. And that's why you might hear that it's easier to boil water on top of a mountain. That's because the atmosphere on a mountain is lighter. There's not as much atmospheric pressure, so water doesn't need to make as much vapor pressure to equal the atmospheric pressure. And so we can represent a lot of this information using a phase diagram. And a phase diagram is just a method of representing the phases of a substance as a function of temperature and pressure. So we have the phase diagram of water here. And let's say you are given this temperature and this pressure, you could tell me that it's going to be at the liquid phase. So phase diagrams are going to be very helpful when determining what phase a substance is going to be at a given temperature and pressure. And there's a bit of new vocab here. First of all, the triple point. The triple point is the temperature and pressure at which solid, liquid, and gas phases can exist. It sounds crazy, but like of water, you can see in this diagram right here, it's kind of hard to see because it's small, but there's some water vapor there that's just floating. You have ice and you have liquid. So at that triple point, all three of these phases can exist at the same time. And then you have the critical point. The critical point is the temperature and pressure above which the liquid and gas state are indistinguishable. So there's not very many pictures of supercritical fluids. Supercritical fluids are what you call the substances that are at the temperature and pressure above which the liquid and gas states are indistinguishable, right? So we can see the supercritical fluid of carbon dioxide, and you see you have a liquid and a gas, but as you continue, this substance is indistinguishable. You don't know if it's a liquid or if it's a gas. And so the critical point, past the temperature and pressure of the critical point, you're going to have supercritical fluids. Now, water is a very special case. If you see this line here, you might wonder why it's dotted. And the reason is because water is one of those weird exceptions where the liquid form of water is more dense than the solid form of water. That's why you see like ice floating on the top, and that's why you have life in like super cold lakes and stuff, because the ice is blocking it, but there's water underneath. What a normal phase diagram looks like for most substances is something like this. So you have a positive slope, if you will, here, but in a water you have a negative slope. And that negative slope is because solid water is less dense than liquid water. All right, let's go through a bit more vocabulary. So when you go from a solid to a liquid, that's called melting. Solid to a gas, so solid to a gas is called sublimation. Liquid to solid is called freezing or solidification. Liquid to gas is called boiling. Gas to solid is called deposition. And then gas to liquid is called condensation. So the two that you probably didn't know are sublimation and deposition, because the other ones are pretty normal in everyday speaking. But when describing phase, it's helpful to know some of these vocab terms. Let's do a bit of practice. The diagram is a microscopic view of a snapshot of a substance at equilibrium, with the circles representing the molecules and the arrows, the molecules' velocity. What state of matter is depicted? I mean, the fact that we're talking about liquids should tell you what phase this is, but you can see from the diagram that the molecules are somewhat close to each other, and they can move around a little, and that's very characteristic of a liquid. And a liquid is the answer. Okay, next up. The melting point of water decreases with increasing pressure. What is the best explanation for this observation? The reason water here is an exception is because when you increase pressure, that means your melting point should go up, not down, because when you increase pressure, you need more vapor pressure in order for the vapor pressure of the liquid to reach atmospheric pressure. And so in order to create more vapor pressure, you would usually need to increase the temperature. But in this case, when you're increasing pressure, the melting point decreases, meaning you need less heat. This wouldn't make sense for other substances because their solid form is more dense than their liquid form. But liquid water is one of those exceptions where it's more dense than its solid counterpart. And that's what creates that weird exception. And therefore, the answer to this question is going to be A. Liquid water is denser than solid water at 0 degrees Celsius. Okay, next. A portion of the gas phase diagram of elemental sulfur is shown below. What statement about sulfur is correct? Okay, let's go through these. Rhombic sulfur cannot be sublimed without first converting to monoclinic sulfur. Sublimed means solid to gas. So we have a rhombic sulfur right here, and we can sublime it into a gas. We can just at low pressure, we can just increase temperature, and that'll sublime it. So this is not true. The conversion of rhombic sulfur to monoclinic sulfur is exothermic. Well, let's look at rhombic sulfur to monoclinic sulfur, right? In order to go from rhombic to monoclinic, you need to increase temperature. And when you need temperature for a reaction, that is characteristic of an endothermic reaction. An exothermic reaction is a reaction where energy is given off, right? But in an endothermic reaction, you need energy for for something to happen. So that means B cannot be the right answer. Let's take a look at C. Rhombic sulfur is denser than monoclinic sulfur. Let's come back to that. At atmospheric pressure, monoclinic sulfur cannot be in equilibrium with liquid sulfur. So at atmospheric pressure, that's this line right here, monoclinic sulfur cannot be in equilibrium with liquid sulfur. That's not correct. We have an instance right here where it's in equilibrium. It's on the line, therefore both of them can exist at the same time. And that means C has to be the right answer, but let's take a look at why. So why does this happen? If we take a look at how to get from monoclinic sulfur to rhombic sulfur, we see that we would need to decrease temperature and increase pressure. In most cases, in order to go from monoclinic to rhombic, you would need to decrease the temperature and increase the pressure. And as it turns out, density is proportional to pressure, but it's inversely proportional to temperature. So when you decrease temperature, you are actually increasing density, and when you are increasing pressure, you are also increasing density. So compared to monoclinic sulfur, rhombic sulfur is going to be more dense. And we are correct. All right, let's move on. A portion of the phase diagram of uranium hexafluoride is shown below. Which statements are correct? UF6 sublimes at atmospheric pressure, and at 80 degrees Celsius and 1.5 atmosphere only the gaseous form of uranium hexafluoride is present at equilibrium. Okay, let's look at one first. UF6 sublimes at atmospheric temperature. Atmospheric temperature is at 1 atmosphere. And so we see that we go from the solid state. The solid state is represented with this section. And then we can go to the gaseous state. And that is sublimation. So yes, we can do what one says. We can sublime UF6. And let's look at the second one. At 80 degrees Celsius and 1.5 atmospheres, 80 degrees and 1.5, so that's going to be right here. And this portion is the gaseous portion. So UF6G is present at equilibrium. That is true. Only the gaseous form is going to be present at equilibrium, and therefore both I1 and 2 are correct. So the answer is C. And we are correct. Moving on, the critical point of carbon dioxide is 304 Kelvin and 73 atmosphere. Under which conditions is carbon dioxide a liquid? Remember what a critical point is. So if you have your phase diagram like this, your critical point is going to be right here. And in temperatures above and pressures above this, you're going to get a supercritical fluid. The liquid's going to be here, gas over here, and the solid's over here. This represents pressure, this represents temperature. So if you are here right now, in order to get to a liquid, you're going to need to decrease the temperature. So let's look at which one of these answer choices decreases temperature. One says 303 Kelvin and 73 atmospheres. So it keeps pressure the same, but it decreases the temperature, which is exactly what we need. One will work. Let's take a look at two though. 305 Kelvin and 74 atmospheres. So that means we're increasing temperature and pressure. We're going to go into the supercritical area. And that supercritical area is not really a liquid. So the only one in which carbon dioxide is going to be a liquid is going to be 1. So 1 only, A. And we are correct. Second to last one, Which of the following would lead to an increase in the vapor pressure of a liquid? So remember our diagram here, where you have a bunch of molecules, and in order for them to jump up and become vapor pressure, they need enough kinetic energy. And so how can we increase kinetic energy? We can increase the temperature. Increasing the temperature is gonna increase the average kinetic energy of all the molecules, and by chance they're gonna have enough energy to jump up and become vapor. Let's take a look at 2, adding a non-volatile solute. Remember, a non-volatile solute is something that's going to have low vapor pressure, meaning there's going to be less molecules that become vapor. And so adding a non-volatile solute is the exact opposite of what we want. A non-volatile solute is going to lower the vapor pressure of our liquid. And so the only answer that works is 1, and therefore the answer is A. And we're correct. Let's move on to the last one. The normal boiling point and vapor pressure at 25 degrees Celsius are measured for liquids in 2 flasks. Flask A contains pure water and flask B contains 1 molar aqueous NaCl solution. Which flask contains the liquid with the higher boiling point? Which flask contains the liquid with the higher vapor pressure? Okay, so let's do the first part, the boiling point. Remember, boiling point is going to be based on intermolecular forces. So we're basically asking ourselves, what's going to have more intermolecular forces, H2O or NaCl? And although water is going to have some hydrogen bonding, it's not going to really fare up with the ionic bonding that's present in salt. So flask B is going to have the higher boiling point, meaning we can cross out A and B. And now let's take a look at which liquid is going to contain a higher vapor pressure. Vapor pressure and boiling point are almost opposites of each other. And so the liquids with a higher vapor pressure are going to be the ones with the lower intermolecular forces. Because if you have lower intermolecular forces, you don't need as much energy to jump up from the surface of the liquid and become that vapor. And so we've already established that NaCl has stronger intermolecular forces, and therefore H2O is going to have higher vapor pressure. So we determined that higher boiling point is going to go to flask B or the NaCl, but the higher vapor pressure is going to go to flask A or the water, and that is C right here. And we are correct. That's all I have for this lesson. I hope you learned something, and I'll see you later in part 4.